All right, I have a hollow conducting spherical shell. The inner radius is r sub I, the outer radius is r sub O, and this sphere has been given some positive charge, capital Q. What we want to do is plot what the potential V looks like as a function of radius, and then also what the electric field looks like as a function of radius. We'll start with the potential. So I'll make a plot of potential versus radius, little r, and there are a couple potential radii that we want to note. So we'll say that's where the inner radius is, and that's where the outer radius falls. Now, in thinking about this, the boundary condition for electric potential for a conductor when it's in electrostatic equilibrium is that the potential has to be constant all throughout the conductor. And we can even calculate what that value is going to have to be, because we know the surface potential is going to have to match the potential that's seen right outside the sphere. So we'll call that V0, and that value is going to be K capital Q over the outer radius, R0. So that potential value is constant for all the radii until we run out of conductor. So I have a constant flat line, and then once I reach the outer radius of the conductor, I know that this is going to have to fall off because it's going to look like a point charge. So it's going to fall off with a dependence proportional to 1 over r. So the potential out here, let's say at this point, corresponding to that radius r, is going to be a value of kq over r. So inside the conductor, the electric potential is constant, and then once you're outside of the conductor, it's going to look the same as the potential due to a point charge. Let's do the same thing, but now let's plot the electric field as a function of radius. So there's my y-axis is electric field magnitude, and my x-axis is going to be for radius. And let's note our two special radii, the inner and the outer. Oops. Okay. Now inside the conductor, we know the electric field is 0. We also observe that the potential is constant. Therefore, the difference of potential is 0 and the electric field is 0. So all throughout the conductor, I'm going to have an electric field that's 0, and then I run out of conductor, and that's where the surface charge is, and that surface charge density on the outer surface of my conductor is going to make a discontinuity in the electric field. It's going to shoot up to some value. We can write that down in a second. And then outside the conductor, it's going to be the electric field from a point charge. So it's going to fall off as proportional to 1 over radius squared. Alright, so first off, let's note what this surface electric field value is going to be. So what should this value be? E0? Well, that's going to be K, the charge on the sphere, over the outer radius squared. And then once I'm outside of the conductor, let's see if I pick, I want to know what the value is there. It's some radius r. That's going to be an electric field, just for what you would see for a point charge q, kq over the distance away squared. As an exercise for yourself, you should go through and determine what these plots of potential versus radius and electric field, magnitude versus radius, are going to look like. Instead of being a positive charge, we charge the sphere so that it is negative. So try that out on your own.